All right, so the last for this chapter will be the evidence of evolution, and this will kind of move around a bit, but there's lots of pieces of evidence. One is natural selection in response to introduced species. Things adapt, things change, and so here we have a soapberry bug, and what you can see is its beak, its little nose has to be long enough to get into through the skin and toward the seed in the middle to get nutrients. And what has happened is there has been a balloon vine that has been fruit that has been introduced, and what you see then is for it to use that, there has been a shift in beak length. And again, this is evidence of evolution, that changes have occurred to deal with new food sources. And again, it took maybe a while. They don't give you a time on here, but it doesn't take a heck of a lot of time for this to happen. So there's one piece of evidence. Another one is the evolution of drug-resistant bacteria. It's probably one of our best, one of the problems we're going to have in the future because of the over prescription of prescribing of bacteria and for things that we aren't sure you have, and from people not taking the full dosage. And so we're ending up with drug-resistant bacteria, and here you can see a chromosome where you see some resistance that has been built up in a bacteria. And over on the right, this is a type of staph infection that MRSA, basically that the antibiotics do not deal with anymore. And you can see on this person's back that basically antibiotics are not fighting this because it has evolved very quickly, drug resistance. All right, another piece of their evidence is comparative anatomy, homologous structures, and this is kind of the magic picture that everybody shows you. These are mammal front limbs, and what you can see is they look quite a bit different. The hand, a cat's front leg, a whale's front flipper, and a bat's wing are all homologous structures, and we all have the same types of bones. They all exist, but you can see by looking that those bones are different shapes, and that is because form follows function. And so although they look quite a bit different and they're used for different reasons, we are all mammals. We do have a common ancestor, and we have very similar bones. And again, they've been highly modified for our way of life. Comparative embryology, some of the things in vertebrates especially, we have pharyngeal arches that are used in chicks and humans. Those pharyngeal arches in fish would actually become fish gill supports. In us, some of those will actually evolve into your jaw. Although we don't really have, pharynxes. We have a pharynx now, but we don't have these structures like some of that show up in our embryos. And also the postanal tail, vertebrae past the anus. And again, we really don't have a tail in us. Monkeys do, but the great apes don't, and birds do, but birds' tails are not what you think they are. Birds' tails are very, very small. They have long tail feathers maybe, but their tails themselves are fairly short. But we can look at the embryos. They look very similar when they start out, and then obviously major changes come. And then biogeography, where things live. That's another great way of looking at things. Things are separated. We have a sugar glider and a flying squirrel. This would be called convergent evolution. Two organisms that look very similar to each other, but one is a marsupial, kind of like the koalas and kangaroos, and a flying squirrel is a placental mammal like we are. And so you can see that they have evolved separately on two different continents. Convergent evolution, obviously this is a good way to look and be in a certain habitat. But biogeography gives us evidence that most of the marsupials that are left on the planet are in Australia. And it's because of Pangea breaking up. You can see that on the picture on the left. What happened is placental mammals started to evolve in South America. And as things started moving around, placentals seem to do better than marsupials in survival rate, but there were no placentals on Australia by the time it moved far enough away to say segregated. So you can kind of map how things have changed as the planet has moved, the continents have moved around. And that gives us evidence of changes in evolution. And then the fossil record obviously is a strong component. It's not perfect by any means. There are things missing, but we can see here whales are actually related to deer, and most people lose their mind. What? And hippos, they're even-toed. Even-toed ungulates. Ungulates are typically deer. Single-toed would be things like horses. They're a little bit different. And so you don't think about it, but if you look at the fossil record, there are fossils of these organisms showing the animal going back into the sea and the modification of the back end into flippers. And so over here on the left would be what we consider to be one of the very early common even-toed. This is a fossil artist rendition of a fossil record from an even-toed. And so you can see most mammals have this double even-toed ungulates up on top. And then the change maybe on the bottom where you have one or two. But anyway, so these are all kind of lumped together, showing that this bone for whales are more closely related to pigs and deer than they would be to anything else. All right, and then the last one is comparative molecular biology. And now we're looking at the DNA and the proteins. And so on the left is a picture of molecular data and proteins and how many number of amino acids differ from a human to some of these other animals. And there's 8 differences from us to a rhesus monkey. Rhesus monkeys are the ones we often do research on. And then we have mouse, chickens, lamprey, which is a jawless fish, early vertebrate. And you can see those numbers increase as we get farther and farther away. Our closest living relatives are the chimpanzees, and here you can see where they think we branched. And I tell you this because with a bonobo chimp, or pygmy chimp is the other common name for these, we have 98% of our DNA is the same as theirs. So that 2% makes a difference. Obviously, the difference between you taking my class and maybe you sitting in a zoo somewhere throwing crap at people, but there is only a 2% difference. And with that, we'll stop the share and stop the recording of this section.